Many students find meter bridge numericals confusing because they are not sure how to connect them with the Wheatstone bridge condition. In this video, we will solve the problem shown on the screen step by step and understand the concept clearly. Welcome to the Current Electricity Numerical series. This is the third video in the series. We are given that the resistance Y in the meter bridge is 12.5 ohms. The bridge is balanced when the length L1 is 39.5 centimeters. Our goal is to find the resistance of X. This question also has a few additional parts. We will solve those later in the video. First, let us convert the meter bridge into its equivalent circuit form. The thick copper strips in the bridge have negligible resistance, so we can treat them simply as connecting wires. Now, consider the meter wire between points A and C. The jockey divides this wire into two segments. The first segment has a length L1, which is 39.5 centimeters. The remaining part of the wire has a length 100 minus L1. Each segment of the wire behaves like a resistor. For a wire with resistivity ρ and cross-sectional area A, the resistance is given by ρ times L divided by A. So, the resistance of the left segment of the wire becomes ρ times L1 divided by A. Similarly, the resistance of the right segment becomes ρ times 100 minus L1 divided by A. Now, we can rearrange the circuit into the standard Wheatstone bridge form. In this form, the four arms of the bridge have the resistances X, Y, ρ times L1 by A, and ρ times 100 minus L1 divided by A. If you are not completely comfortable with the Wheatstone bridge concept, I recommend watching my video explaining it. You will understand the idea clearly in about 10 minutes. Now we apply the balanced Wheatstone bridge condition. At balance, the ratio of resistances in one branch is equal to the ratio of resistances in the other branch. So we can write X divided by ρ, L1, by A equals Y divided by ρ times 100 minus L1 divided by A. Now, notice that the terms ρ and A appear on both sides of the equation, so we can cancel them. This simplifies the expression to X divided by L1 equals Y divided by 100 minus L1. We know that Y is 12.5 ohms, and L1 is 39.5 centimeters. Substituting these values, we get X equals L1 times 12.5 divided by 100 minus L1. Now, substituting the numerical values, X equals 39.5 multiplied by 12.5 divided by 60.5. This gives X equal to 8.16 ohms. Now let us move to the second part of the question. Why are the copper conductors in a meter bridge made thick? We know that the resistance of a conductor is inversely proportional to its cross-sectional area. In a Wheatstone bridge experiment, we want the connecting wires to have negligible resistance so that they do not affect the calculation of the unknown resistance. Copper is used because it has very low resistivity. The conductors are made thick so that their cross-sectional area is large, which further reduces their resistance. This keeps the setup close to an ideal Wheatstone bridge and improves the accuracy of the measurement. Now let us move to the next part of the question. It asks, if the resistors X and Y are interchanged, what will be the new balance point? Let us assume that the new balance point is at a distance L2 from point A. Using the same reasoning as before, we can write the Wheatstone bridge balance condition. So we get Y divided by ρ, L2, by A equals X, divided by ρ times 100 minus L2, divided by A. Again, the terms ρ and A appear on both sides, so they cancel out. This gives Y divided by L2 equals X divided by 100 minus L2. Let us call this equation 1. Now we substitute the known values of x and y and solve for L2. This gives the new balance length. L2 equals 60.47 centimeters. If you observe carefully, the balance lengths are also interchanged when the resistors are interchanged. In fact, L2 is simply equal to 100 minus L1. This result is consistent with the balanced Wheatstone bridge condition. Now, let us move to the final part of the question. It asks, what happens if the galvanometer and the cell are interchanged? Will the galvanometer show any deflection? To analyze this, let us swap the positions of the galvanometer and the battery in the circuit. Now, we again apply the Wheatstone bridge balance condition for the two sides of the galvanometer. So we can write x divided by y equals rho times 100 minus L2 divided by A, divided by rho times L2 divided by A. Again, the terms rho and A cancel out. This gives x divided by y equals 100 minus L2 divided by L2. Rearranging this expression, we get y divided by x equals L2 divided by 100 minus L2. Further rearranging, we will get y by L2 equals x divided by 100 minus L2. But this is exactly the same relation we obtained earlier in equation 1 while calculating L2. Therefore, swapping the galvanometer and the cell does not disturb the balance condition, so the galvanometer will still show zero deflection. This completes the solution to problem. If this explanation helped you understand the concept, please share this video with your friends and classmates. Subscribe to the channel for more physics numericals and concept-based explanations. And if there is any physics problem you would like me to solve, let me know in the comments. I will solve it in one of the next videos. Thank you for watching, and see you in the next one.